Thank you very much for the kind introduction. And I would like to thank Professor Bishlawi for the kind invitation. I'm pleased to be here with you for the first time. So I'm a PhD candidate in Milan. I'm Lebanese based in Milan, studying for my degree in Translational Medicine with a focus on beta-thalassemia. And my work is actually on oxidative stress and beta-thalassemia. So today we'll be giving an overview about redox balance and oxidative stress and beta-thalassemia, a topic that has been discussed if you go back into the literature years back. We've seen many studies, and then for some reason the work on oxidative stress stopped, so we're trying to revive back the field. So I'll be going quickly over some introduction, talking about sources of reactive oxygen species in red blood cells, talk about intracellular damage due to oxidative cells in RBCs, focus on the mechanisms of oxidative stress development in beta-thalassemia, talk about antioxidant enzymes and cytoprotective defenses that we have, talk in general about general antioxidants, which was brought up a lot today, and the role of targeted and individualized therapy. So looking at oxidative stress and beta-thalassemia, we know that while it's not one of the main primary etiologies of the disease, it really plays a very significant role in the pathogenesis of the disease. And we're going to see throughout this presentation why and how. And we know that there are different mechanisms that exist behind the development of oxidative stress, and we're going to go over these throughout this presentation, but the ultimate result is cytotoxicity. And we know that sources of reactive oxygen species production in pathophysiology are not only disease-specific, but they can also be organ-specific, meaning that the same source, the source of reactive oxygen species can be different if you look at one organ compared to another. And if you look at the image on the right side of the slide, we can see that in cells in general, we have different sources of reactive oxygen species. And these include the mitochondria, NADPH oxidases, cyclooxygenases, lipoxygenases, cytochrome P450, xanthine oxidase, and uncoupled nitric oxide synthase. So looking at sources of reactive oxygen species in red blood cells, if we start from left to right, you can see that the process of autooxidation from oxygenated hemoglobin to methemoglobin is one of the main processes that actually occurs in beta-thalassemia due to instability of hemoglobin molecules, and this leads to ROS production and oxidative damage. But we can also see that iron, whether it's in its free form or bound to heme and hemoglobin, can also act as part of the Fenton reaction, the Haber-Weiss reaction, and cause oxidative damage. And on the right side, you can see that some heme-derived oxidants induce the recruitment of platelets, leukocytes, and red blood cells, leading to lipoprotein oxygenation and consumption of nitric oxide. And this is often seen in vascular endothelial cells, and this leads to a pro-inflammatory response, oxidative damage, and this is what we commonly see as a procoagulant phenotype that we often see in beta-thalassemia. If we focus again on the role of heme as a source of reactive oxygen species, you can see that heme can actually cause oxidative denaturation to DNA. It can activate pro-apoptotic events like caspases and caseptins. It can impair mitochondrial function, and it can overcome some of the antioxidant mechanisms and cytoprotective mechanisms that we actually have, and all these in turn will lead to oxidative damage. So next we'll discuss some oxidative damage through some intracellular components of the red blood cells, and we're going to focus on membrane cytoskeletal proteins. So we have different membrane cytoskeletal proteins involved in these RBCs: spectrins, protein 3, protein 4.1, ankyrin, globin, so we have many. Just to give you an example, that spectrins themselves might be actually targeted by oxidation, and this, what actually happens is that this perturbates their interaction with other cytoskeletal proteins like actin, or with other multi-protein complexes in the membrane of the cytoskeleton, and cause disruption of the cellular membrane. And some of the proteins involved include protein 4.1 and band 3, and this leads to an impaired stability in the interaction between the cytoskeletal protein and the cellular membrane. So looking specifically at band 3, the band 3 protein, we know that oxidation-induced damage and abnormal clusterization of this band 3 protein will actually increase the fragility of the red blood cell, so the red blood cell will become more fragile, and we have a generation of erythroid microvesicles that can contribute to the procoagulant phenotype that we mentioned earlier, as seen in beta-thalassemia. Next, we move to membrane lipids, and we know that lipid peroxidation and protein oxygenation, they disrupt the organization of the lipid membrane. And once this happens, we will have cellular deformity, and we will have the phosphatidylserine molecules exposed to the outer cell membrane of the cell, and this will turn on the macrophages to come and phagocytose the exposed red blood cell, and this is the mechanism where we see red blood cell removal during eryptosis, and this is actually exacerbated even further when we have a state of oxidative stress. So moving now into the different mechanisms of oxidative stress in beta-thalassemia, we start with oxidative stress and hemoglobin instability. And we know that actually in beta-thalassemia, we have an unbalanced production of globin chains, which starts on at the early pathophysiology, and this results in excess free alpha globin chains. And these unstable free alpha globin chains will actually auto-oxidize, denature, and precipitate in hemichromes. And as you can see in these pictures, once we have precipitation of these hemichromes, they will actually come and bind to this band 3 protein, which we actually spoke about being found on the membrane of the red blood cell. It will be oxidized, so it forms a hemibound band 3. It oxidizes, it then phosphorylates, and then it forms a hemibound cluster, band 3 cluster. And upon the formation of this cluster, as a result of this hemichrome binding, we have a self-amplifying redox reaction that actually can oxidize even more additional hemoglobin molecules. It will deplete the cell from its reduction potential, and it will trigger some phosphorylative responses that lead to more destabilization of the cellular membrane. And this is why this is very important. What about oxidative stress and ineffective erythropoiesis? We know that ineffective erythropoiesis is actually attributed to the presence of some extra unpaired alpha globin chains. And this has the tendency to precipitate, auto-oxidize, and produce high amounts of reactive oxygen species. So oxidative stress actually starts really early on in the ineffective erythropoiesis process. And many studies have actually showed that the presence of these alpha globin precipitates are actually present in cells at the polychromatophilic stage of erythropoiesis. And this stage is actually characterized by increased hemoglobinization and increased apoptosis in beta-thalassemia erythropoiesis. What about oxidative stress and iron overload, which has been spoken a lot about today? We know that iron overload is one of the main complications in beta-thalassemia, whether we're talking in TTT or NTDT, and it can cause a lot of damage. So basically, as a result of this increase that we see in iron overload, we have transferrin becomes saturated. And when transferrin becomes saturated, we have non-transferrin bound iron and labile plasma iron that will enter the organs through several divalent cation channels, ion transporters, such as the MT1 receptors, such as L-type calcium channels, and they actually can cause cellular damage. And actually, what actually happens as well is we can have a case of lipid peroxidation causing ferroptosis, necrosis, and apoptosis, ultimately leading to cell death. So iron overload, induced oxidative stress, is the most commonly seen form of oxidative stress. However, we see that there are different mechanisms by which it develops, not only as a result of oxidative stress, and it's found everywhere, all throughout the pathophysiology of the disease itself. Moving next to some antioxidant enzymes and cytoprotective defenses in beta-thalassemia, we'll start with peroxyredoxin 2. Peroxyredoxin 2 is actually a cytoprotective enzyme. There have been many studies that have actually studied peroxyredoxin 2. However, for the sake of this presentation and for the sake of time, I'll be just only giving one example. This study actually looked at the activity of peroxyredoxin 2 in thalassemic mice versus thalassemic mice with a knockout of the peroxyredoxin 2. And as we can see, the absence of peroxyredoxin 2 actually increased beta-thalassemia ineffective erythropoiesis and iron overload in the mice that lacked this particular enzyme. And this actually tells us why this enzyme is actually important. Looking further into the data, they not only looked at ineffective erythropoiesis, but its absence not only worsened ineffective erythropoiesis, but it also led to an increase in ROS levels, and it also led to cell apoptosis as well. The next set of antiprotective enzymes and antioxidant enzymes that we're going to look at are superoxide dismutase and catalase. And these work in synergy, they work together. So the first step is the superoxide dismutase enzyme will catalyze the reaction of oxidative radicals, leading to the production of a less reactive hydrogen peroxide molecule. And then catalase will come and catalyze the reaction of hydrogen peroxide to produce water. So several studies also looked at in patients. They looked at superoxide dismutase levels and catalase levels in thalassemia patients. For example, this study conducted on transfusion-dependent patients found that SOD levels in thalassemic patients were higher compared to healthy controls. And the study on the left side showed a different story. They actually showed that SOD levels were not so significantly different between healthy controls and transfusion-dependent patients. And the study on the right side actually showed even the opposite. Low levels of SOD were reported in transfusion-dependent patients compared to healthy controls. So what does this mean, and why do we have this contradictory information between various studies in the literature? We still don't know why we have these varying levels of data being reported. However, we think that further studies need to be conducted in this field with this bigger sample size and a more unified methodological approach with similar inclusion-exclusion criteria to really be able to study well the levels of these enzymes in thalassemia patients. The next system I want to discuss is the glutathione system. The glutathione system is also a very important cytoprotective defense mechanisms that we see in beta-thalassemia. And we've also had several studies that looked at the activity of the glutathione system and its enzymes. For example, this study actually reported that patients, as a result of iron overload, showed a decreased GSH-GSSG ratio, and it showed an increase in the activity of the three enzymes involved in the glutathione system. These are the transferase, the reductase, and the peroxidase. And this actually tells us that these enzymes are working and are fighting off the oxidants. This is why the levels are actually high in thalassemic patients compared to normal subjects. The last antioxidant enzyme and cytoprotective defense mechanism I want to talk about is heme oxygenase 1. So we know that the catabolism of heme is also important, both in normal and pathologic erythropoiesis, and we saw at the beginning of the presentation why heme can be actually a source of reactive oxygen species in red blood cell. So we know that heme actually that is derived from hemoglobin can actually be degraded by this enzyme heme oxygenase 1 to produce iron, carbon monoxide, and biliverdin, which then gets converted to bilirubin. And these products of this reaction are actually good because they are anti-inflammatory, antioxidative. So heme oxygenase 1 is doing its job here to turn something that is pro-oxidant to some compounds that are eventually antioxidant. However, in 2018, one study published in Blood in 2018, they said that, okay, heme oxygenase 1 seems to be doing its job, it's great, but let's not forget that one of the products of this reaction is what? It's free iron. So they came and said, this reaction that's catalyzed by heme oxygenase 1 is releasing iron, and we know that iron is actually a potent pro-oxidant. So what they came and what they did in the study is they actually administered a heme oxygenase inhibitor that we call 10-protoporphyrin 9. And what happened is among the administration of this inhibitor to a mouse model of beta-thalassemia, they used the HBB-TAL3 model, which mimics non-transfusion dependent thalassemia. Upon administration of this inhibitor, we saw an improved in hematological parameters, decreased anemia, improvement in ineffective erythropoiesis, decreased liver iron concentration, decreased apoptosis, alpha-globin precipitation. We saw an increase in red blood cell lifespan and serum hepcidin levels. So this inhibitor seems to be doing a good job. But then again, there comes the debate. So what should we do? Should we inhibit the heme oxygenase activity, because ultimately it's doing a good role in preventing this heme from being a pro-oxidant molecule. Next, we move to antioxidant therapeutic agents. So we have many general antioxidants that have been reported in the literature. We know about all of these: vitamin C and E, flavonoids, curcumoids, and acetylcysteine. Many of these have been used in transfusion-dependent, non-transfusion-dependent, and even sickle cell disease patients. But the main point or argument of this presentation is, why should we move from general antioxidants to targeted therapy, and what are the pitfalls of general antioxidants? So yes, general antioxidants, we know that they can remove both intra and extracellular iron species that are generating these radicals. But we have to know that as well, that although reactive oxygen species are associated with injurious processes, their presence is essential for cellular function. Because these molecules can be specific mediators, they can act as second messengers of cell signaling, and these play a role in vascular tone, immune responses, cell protection, gene transcription, and hormonal actions. So yes, if you would like to administer general antioxidant, fine, but you have to be careful, because what happens when you administer general antioxidants, you might be solving the problem that you see, but at the same time, you don't know what else is decreasing in the body. You're messing up the whole physiological redox balance that's already found. And if you're not careful, lowering the levels of ROS to a certain level, it becomes very detrimental. And so this way of thinking paved this way of thinking, led me to think about what about if we actually look into specific sources of reactive oxygen species in beta-thalassemia, which wasn't really done too much before. And I decided to look at the cytochrome P450 molecule, and this is my master thesis data, which I'll be presenting to you just as a proof of concept of how we can connect these unmet needs that we saw at the preclinical molecular level and translate them into better findings for the future for our beta-thalassemia patients. So just a background on the cytochromes, for those of you who don't know the cytochromes, they belong to a large family of hemoproteins that are predominantly involved in the metabolism of both endogenous and exogenous substances. They are bound either to the membranes of the endoplasmic reticulum or the mitochondria, and they are known to play a role in different redox reactions. And they've been shown to be major sources of reactive oxygen species with different implications in different disease conditions. And one of the physiologically relevant reactions catalyzed by cytochrome P450 is arachidonic acid metabolism. How it works? So we know that the activation of phospholipase A2 from the phospholipid membrane will actually induce the release of free arachidonic acid. Now this free arachidonic acid is then metabolized by the monooxygenase pathway through cytochrome P450, and specifically through two subfamilies of the cytochromes. On the blue side, you can see that it's metabolized by cytochromes 4A and 4F, which belong to the hydroxylases, to produce a metabolite that we call 20-HETE. And on the red side, you can see that it can also be metabolized by cytochromes 1A, 2B, 2C, and 2J, which belong to the epoxygenase family, to produce another metabolite known as EET. So, for the sake of my experiment, I decided to focus on one pathway first, and I actually looked at the hydroxylase family of cytochromes. And what we found is we actually conducted this experiment on the HBB-TAL3+ model, which mimic non-transfusion dependent thalassemia, and we specifically looked at the liver. And when we measured the expression of these cytochromes, when we looked at the expression of these cytochromes at the level of mRNA, we did not really see any significant differences in cytochromes 4A and 4F expression levels in thalassemic mice compared to normal wild-type mice. However, as it was at the level of the protein, as you can see on this side, on the right side, we saw a very significant increase in the level of these cytochromes in thalassemic mice compared to control. And to further confirm our data, we did an immunohistochemistry assay where we looked at the cytochrome 4A expression level in the tissue sample of the kidney. And as you can see in this image actually represents a section of the liver around the central lobular area of the brain. And as you can see by the intensity of the coloration, the picture on the right side is the thalassemics, the picture on the left side is the wild-type mouse, and you can see from the intensity of the coloration, we have overexpression of these cytochromes in the liver. We then measured, of course, the metabolite that's produced by these cytochromes 4A and 4F, which is known as 20-HETE. And 20-HETE, based on many studies published in the literature, not in the context of thalassemia, in the context of other disorders, is actually a bad metabolite. And you can see how significantly high it was in the thalassemic mice compared to normal control mice. Then we wanted to see, okay, what's the effect of this iron overload-induced oxidative stress from cytochromes doing to the liver? And so we looked at these liver tissue sections, and we measured using H&E and mass trichome staining. We looked at inflammation and fibrosis, and we actually could see signs of inflammation and fibrosis in the thalassemic mice compared to control. So actually, we were the first to describe the role of cytochrome P450 being involved in beta-thalassemia. Of course, this does not rule out the presence of other specific oxidative stress markers or sources of reactive oxygen species. If you remember at the beginning, we saw the picture of the cell with so many sources. I happen to have decided to start with cytochrome P450, and this is what I found. But then we have 7 others that we need to look at and test even further, not only in the context of beta-thalassemia, but also in sickle cell disease. Because of the similar pathophysiology, we have a lot of similarities between these two disorders. And so we published our data. And my takeaway messages are from this presentation that while oxidative stress is not among the primary etiologies of beta-thalassemia, it really plays a very significant role in the pathogenesis of the disease itself. And we showed through several mechanisms how it's involved, and it's involved everywhere, basically, not just as a result of iron overload. The mechanism of oxidative stress development is not only multifactorial in nature, but it's also different, and it can differ from one organ to another. We know that oxidative stress can be ameliorated with antioxidative treatment modalities that act at various levels. So yes, general antioxidants have proved to be effective However, is it the best therapy? And ultimately, based on the current research that it's actually ongoing as part of my PhD program, I'm trying to understand better the role of the cytochrome, the pathways involved, and then try to move to a more targeted ROS approach, of course, in combination with the current conventional treatment modalities that are available for patients. Obviously, the identification of cytoprotective and antioxidant enzymes and molecules has really paved the way for a new era of new pharmacological targets for treating beta-thalassemia patients. So I showed you, for example, different enzymes and cytoprotective mechanisms from these enzymes involved, but more research needs to be done on these enzymes to either activate or inhibit the production of these enzymes. It's how you play with these enzymes, by either activating them or inhibiting them. And it's just a try and see what happens. But as we can see based on the published literature, there's still a lot lacking in the field. And we also have a lot of discrepancy in the reported data in the field. So really more work needs to be done, I think, and more effort needs to be done on these cytoprotective and antioxidant enzymes that we already know of. They've already been reported, but not so many people have really focused on how really important these are. For optimal outcomes, of course, future studies should aim at identifying specific sources of reactive oxygen species and apply targeted and direct therapy and improve overall outcomes for patients. So we've identified some unmet needs with general antioxidants. Based on these general unmet needs in general antioxidants, we're now trying to move into a different field, a field of targeted therapy, applying direct therapy, and move to individualized therapy eventually in the future for patients. And of course, a better understanding of the main oxidants and antioxidants involved and the associated cascade of biological events will provide a better insight to achieve an optimal redox balance. And this is what's important. And at the end, I leave you with this review. This was published just 2 weeks ago, where we actually give a very nice overview of redox balance in not only in beta-thalassemia, but also in sickle cell disease, with some similarities and differences from what we spoke about. And we called it a love and hate relationship because it's a very complex relationship between oxidants and antioxidants. And at the end, I would like to thank my mentor, Professor Ali Tahir, who, because of him, none of this would have been possible. I've been working with him for so many years, and he's a person that I look up to, and all this work was, he was very much influential in my career path in doing basic science and preclinical research in beta-thalassemia. And with that, thank you, and I'm happy to take questions.